Okay, well, welcome everyone to the Quasar session, and glad to have you here. I'm Mike Crenshaw. I'm a professor at Georgia State University. I'm also the current chair of the ARC board, but don't complain to me, just send your complaints to Nancy if anything goes wrong. Just wanted to remind you that if you want to ask questions, feel free to raise your hand either on screen or by icon, or you can put them in the AGN, actually the Quasar channel on Slack, or you can put them in the chat if you would like. Just going to tell the speakers that I'm going to try this background thing where we'll start out with green for 10 minutes, and then the final 2 minutes of your talk will be in yellow. And then when it hits red, that's time for you to make sure you're done and to have a few minutes for questions. Okay, so any questions before we get started? All right, cool. All right, so our first talk is by Joseph Choi from the University of Oklahoma. And he's going to be talking about the physical properties of low redshift Fe Lobau quasars. Anytime you're ready.
All right, sounds good. Wait. All right, everybody can hear me, right? Okay, great. Oh, so thank you for the introductions. So hello, my name is Joseph Choi. I'm a graduate student at the University of Oklahoma. And today I'm going to be sharing with you how our group's been studying quasar outflows using Symbol, which is our own spectrosynthesis code, and how the data from APO has helped us understand quasar outflow phenomenon and contributed to our research. At the bottom of the slide, I list the names of our team members and collaborators. I first want to emphasize that, point out that Dr. Laley and Dr. Turnip and I have been the core writer of the contributor to the code development. And moreover, I also want to point out that right after this talk, there will be 2 additional Symbol talks given by Sophia Pasquini from University of Western Ontario, and there's there's another talk also by Collier Larson from Ohio State University. So stay tuned for those talks as well. So, what are Fe Lobaus? So as we heard from on Monday's talk by Bina, the quasar outflows are a very interesting phenomenon, and they're very important, and they're thought to play a significant role in quasar feedback, and they're frequently seen in either in emission lines or absorption lines, and all the way from the X-ray to radio. And in our group, we're particularly interested in quasar outflows seen in blue shifted broad absorption lines or BALs. And the figure on the top right corner of this slide shows so the outflow gas is traveling away from the AGN, and we'll see a blue shifted absorption lines, the blue shifted relative to the quasar rest frame in the spectra. And about 15 to 40% of the quasar spectra show this outflow BAL features in the rest UV bandpass. And among different subtypes of broad absorption line quasars, our groups are currently particularly interested in this iron low ionization broad absorption line quasars, or Fe Lobau quasars. And these iron Lobau outflows are, as you can assume from the name, show absorption lines from the iron ions and other low ionization ions, such as magnesium-2 and aluminum-3, which I will show in a bit. And these outflows are very interesting than the other subtype of broad absorption line outflows, because they are thought to be higher column density outflows, more massive and potentially more powerful and more significant. And in terms of quasar properties, Fe Lobau quasars are more red than the non-BAL quasars, and even redder than other subtype of broad absorption line quasars. And people have assumed that this quasars might be in the short-lived stage in the quasar evolution, so-called the blowout phase, where they're actively expelling a shroud of gas and dust. And the figure in the bottom right part of the slide taken from the Laley et al. 2018 show how Symbol, the spectrosynthesis code, works. And the detailed explanation of how our code works will be included in the talk by Sophia Pasquini. So moving on to some science results. So I would like to first show you J1352, and I want to share with you how the APO triple spec played a pivotal role in discovery of this most energetic AGN wind ever discovered to date. So it was originally cataloged as a Z of 2 quasar in the SDSS catalog, and the figure on the bottom shows the rest wavelength on the bottom x-axis and the observed wavelength at the top x-axis, and this is corrected using Z of 2. And the dotted vertical line shows where the magnesium 2 emission line at the quasar rest frame should be at, and the shaded region shows where the troughs are located. So from looking at this very impressive trough, we can already assume that it must be very high opacity outflow with high column densities. However, in terms of kinematic properties, this is only the troughs are only blue shifted about several thousand kilometers per second, and that doesn't really translate to energetic or powerful outflows. But however, as you can see from this APOSS spectrum, there are practically no any strong emission lines to accurately measure the redshift from. So we followed up this object using APO triple spec and as well as Gemini geners, and we're able to get a way more reliable and correct redshift estimate for this object. So Z of 2.26, about 10% greater than what's previously known for this one. And that puts this trough in way more blue shifted than previously thought at about the tens of thousands of kilometers per second. So using Symbol, we're able to fit the data and get an excellent best fitting model for this one. And we're able to constrain the various physical properties of this object. So first, the outflow velocities, as here and written on the slide, exceeds more than 10% of the speed of light, with the mass outflow rate about 3,000 solar masses per year. And most interestingly, the kinetic luminosity of this outflow, or the outflow energy, actually, from our calculation, exceeds the luminosity, the bolometric luminosity of this object. And aside from measuring accurate redshift, we're also able to measure the black hole mass of this quasar using the Balmer emission lines, which I will explain a little more detail later about how important it is to measure the black hole mass and other properties that we've been measuring in the near infrared spectra of quasars. So this object itself is very impressive. However, it's difficult in order to understand the general physical properties of the Fe low-bow outflows, we need to look at a larger sample and a larger number of objects. So we took a look at the SDSS and BOSS archive, and we gathered about 50 iron low-bow quasar spectra from the SDSS and BOSS survey. And here I'm showing you some of the best fitting models of this 50 objects, and the red is the best fitting model from Symbol, and the black is the data. As you can see, we get in this excellent fit of this broad absorption line quasar spectra. And so x-axis is rest wavelengths and y-axis is half lambda. And from the long wavelength to the short wavelengths, I put in the figure in the different shades some of the absorption lines seen in the spectra, from magnesium 2 absorption lines around 2800 angstroms, and the main iron 2 absorption lines around 2400 and 2600 angstroms, and aluminum 3 absorption lines around 2850. And for the object at the bottom, and I also put some physical properties that we're able to constrain from the best fitting model inside the figure. The object in the bottom also shows this interesting absorption lines from the excited state ions around 2700 and 2500 shaded in brown. And this is because this outflow has way higher number density of gas, the log n of 7.5, and that's why we're seeing other extra emission absorption lines compared to the one at the top. So aside from this moderately absorbed spectra, in our sample, we also have this very interesting objects called overlapping trough bows. They have this very high opacity outflows in the quasars. And we're also able to, as you can see, get a very excellent model fits of these objects. And they have a high opacity, and so they have a very high column density outflows and high density gas. And we also measure the locations of where the gas are located, and they range from a subparsec scale to all the way out to tens of kiloparsec scales. But now shifting to a different bandpass, I would like to focus on the optical part of the spectra. So for a subsample of 30 redshift less than 1 objects, we're able to model the H beta line and oxygen 3 emission lines from the APOSS spectra. And from that region, we can not only measure black hole mass and Eddington ratio, but we can also measure emission line properties, such as equivalent width of iron 3, oxygen 3, or bomber lines. But also we can get the velocity kinematic properties of oxygen 3 line as well, and understand how these optical properties are correlated to the outflow properties that we're able to constrain from the rest UV parts, or we can also understand the general properties of the quasar and the central supermassive black hole and see how that are related to the quasar outflow properties. And interestingly, we discovered this very interesting result that there seems to be two distinct populations of Fe low-bulk quasars in our sample. And the figures in the x-axis is labeled the E1 parameters. It's a derived parameter from the emission line strengths calculated from O3 strength, ion strength, and bomber line strength. And what they basically represent is the accretion rate of these quasars. So E1 less than 0 objects are low accretion, low Eddington ratio objects, and the E1 greater than 0 objects are high accretion and high Eddington ratio objects. And compared to the comparison sample chosen based on the redshift range of our Fe low-bulk quasars and the luminosity ranges, compared to the comparison sample, we see this bimodal distribution where it seems that the iron low-bulk quasars are either low accreting, a low Eddington ratio, or highly accreting. And the bottom two panels show what they look like in the spectrum. So for the low accretion objects, they show a very strong oxygen 3 emission lines with relatively weak iron emissions, and high accretion objects show a relatively weak oxygen 3 emissions and, however, strong iron emission lines. And on top of this optical properties, as I mentioned before, we also included the outflow properties to the analysis to see if we find any sort of interesting correlations between the two population idea. And we do. So for the low accretion objects here plotted in red in the right panel, they also to give you more detail about the plots. The y-axis is log R over RD, basically represents how far the outflow gas is located from the supermassive black hole. So higher log R, the higher the log R, the farther the gas is located from the supermassive black hole. And x-axis represents the kinematic properties of the outflow gas. As you can see, the high accretion objects and the low accretion objects, they show a very different correlation trend between these two groups. And more detailed interpretation and analysis of where this two population idea fits in with the broader picture of quasar evolution, you can find that in this upcoming paper by in Laley et al. Hopefully you'll be able to find that in the archive pretty soon. So where does, so far I've discussed a lot of things that we were able to find from this sample of Fe low-bulks, but where do they fit in with the APO instruments? So the most natural question is, do we expect the similar properties in the high redshift iron low-bulk quasars? And we're interested in question in particular because we know that the quasars were more active at higher redshift around Z of 2. So we want to know whether this, when the quasars are very active and that redshift range, whether those quasars also show similar behavior. But in order to study the H beta and oxygen 3 region, we need to look at the near infrared bandpass, and that's where we've been using APO instruments. So we've been using APO triple spec to get to high signal to noise ratio near infrared spectra of these objects. And we're planning to use request more observing time to continue our research. And moreover, we've been also looking at the APO NICVIPS instrument so that we can, for some of the less luminous object where we have no information of the near infrared brightness, we were looking at, we're using this instrument to get the photometry data so that to help us plan future spectroscopic observations. And also the photometry data also give us information about whether these objects have varied whether they show the temporal variability, which leads to this very interesting object, SDSS J1229, which will be discussed by Sophia Paschini. So in one of the nights, we were able to get a very good quality, high signal to noise ratio of near infrared spectra for this object, where this object is very interesting because it shows a very interesting ion trough variability. And a more detailed analysis, of course, will be explained in the talk after this. And if you have any questions with what we've been doing, how Symbol can help you understand outflows. And so another thing I'd like to add is that hopefully in the near future, the Symbol code will be released so that everyone in the BAL community or the outflow community can use and study this tens of thousands of BAL spectra that are currently available in the SDSS archive. And I'll be happy to take any questions.
Okay, thank you. Great, good talk, Joseph. Appreciate it. Any questions or some claps I see? Any hands raised? Feel free to chime in or to put something on the Slack channel. If there are no questions, I have one.
Yes.
Which is for your really high redshift, really massive outflow object that you talked about first. You got a mass outflow rate of like 3,000 solar masses per year. What did you assume for the geometry or the global covering factor in order to get that number?
So thank you for that very interesting question. That's something that we discuss in depth in the paper. So I guess long story short is that it might be better for me to refer you to that paper, because that's a really highly debated topic, because oftentimes this geometry can be inferred from the statistical analysis of how many FE lobos you can find in the sample, but that can be biased depending on your parent sample, whether you're looking at the IR sample or whatnot.
Curious as to whether it was 5%, 10%, 50%.
So we actually, so because we are using a forward modeling technique, we actually used a range of covering fraction, and more detailed analysis can be found in the paper. So, yeah.
Okay. Thanks. And once again, if there are further questions, please put them on the Slack channel. So our next